My name is Ryan Baxter. I head up the cloud segment within the compute and networking business unit at Micron. I also help out with the CXL strategy. So excited to be here, excited to talk about what excites us, which is data-centric workloads in the future data center. Lots of trends happening in the space, very interesting from a, what used to be versus what's coming around the corner perspective. Yeah, looking forward to a good dialogue here. Another safe harbor statement. I'll give you a couple of seconds to read that. Okay, let's dive right in. So you really can't talk about data center trends without really talking about cloud trends and how far we've come with respect to the evolution of the cloud from what it used to be to what it is today. And what it used to be was probably something similar to a CRM application running on a handful of servers in an IT department at the basement of a corporate headquarters somewhere. What it is now is hundreds of data centers globally deployed around the world to service the public cloud, on-prem cloud, the buildup of significant degrees of compute, both inside corporate data centers as well as colos, and the extension of cloud at the intelligent edge. And we believe the intelligent edge is truly an extension of the perimeter of the data center. So an example there is that Microsoft just yesterday actually announced that it's on pace to build 50 to 100 data centers per year. And these are not just data centers with a few dozen servers inside. These are tens of thousands of servers, multiple phases that are being deployed globally. And what these data centers look like are very different than what they looked like even a couple of years ago to tackle the workloads that are coming at us fast and furious over the next several years. At the end of the day, the data center is morphing. With respect to heterogeneous compute, no longer are we seeing traditional CPUs, memory, and storage, on a cookie cutter, many tens of thousands of those same configurations inside the four walls of the data center. We're actually seeing purpose-built infrastructure where CPU functions give way to XPU functions. And that has a lot of impact on the type of memory that you use, what sorts of factors are important, how do you connect to it, what kinds of power envelopes you're talking about, footprints, things like that just, frankly, aren't anything that you had to worry about just a couple of years ago. Raj and I'll say, AI, it's certainly data generation and doing something useful with it in real time. And what real time to us means is memory. So basically, leveraging the fact that more sophisticated models give you greater insight, but those, getting to those more sophisticated models is not easy, right? You got to really think about how to tackle a very, very new set of problems. Hybrid cloud, on-prem and off-prem domains, and the ability to basically migrate applications across those domains seamlessly. You need application portability. Recent trends of containerization with frameworks like Kubernetes have definitely allowed you to get there. You're moving from a regime of traditional deployment to sort of virtualized deployment that really moved the needle in a lot of ways to now a containerized deployment. And we're really looking at very interesting aspects as to how that plays out in the data center. Intelligent edge, again, I talked about this as an extension of the data center. Essentially, the edge extends the perimeter of the data center. And the physical distance of those compute functions are actually brought closer by the low latency network interconnect, namely 5G that we all know and love, but also the innovation happening on the network side that really drives a lot of value here. Lisa Spellman from Intel recently stated that as early as 2025, 75% of all data being generated is actually generated at the edge. And if you think about that, the importance of compute at the edge and that handshake that you need for those edge devices back into the data center becomes that much more important. And finally, security. Workloads need end-to-end security. And what that means is essentially, we've all been through the various data breaches and whatnot. And so it really is becoming a battleground for cloud providers. And we're starting to see requirements right now that provide or drive encryption even in DRAM. This is something that was unheard of a couple of years ago. Basically, DRAM forgets the information if you unplug it from the server, but nonetheless, customers are really driving for those requirements. So I'll pause. Okay. So heterogeneous compute, it's really driving data center infrastructure, and this is disaggregated and composable. AI training is an example. It requires many compute cores to be efficient. Of course, you could use standard x86 compute cores, and you could get the job done, but it'd be like taking a sledgehammer to pound in a thumbtack. Most people are using things like GPUs and thousands of cores to address this workload. Really what we're talking about is the right side of the foil, the compute need or the floating point operation, and needing not just more memory, but faster memory, higher bandwidth memory, CPU connected memory, as well as XPU connected memory. Again, a lot of that starts to play out in very different characteristics of what you connect to the compute element. Media transcoding. Again, x86 CPUs can do it, but there's more efficient ways to accomplish this. Think of how many messages, how many photos, other content is being exchanged on present day platforms, and leveraging a purpose-built ASIC rather than occupying precious x86 compute cycles for that to be able to use those x86 cycles for something else is really, saving a couple of pennies per transaction. But if you sort of extrapolate that across what the number of transactions happening per person per day across the entire globe, those pennies end up adding up very, very quickly at hyperscale. So it's about the compute growth and the memory capability growing hand in hand. And it really does have significant implications for what tomorrow's memory storage hierarchy needs to look like. So what does the infrastructure of yesteryear look like? It's very defined, highly deterministic. It's really the workhorse platforms that have served us well for many years. But of course, workloads have evolved. The advent of cloud, hyperscale customers engaged in sort of this cloud services war became maniacally focused on efficiency, and it's all about driving that last bit of efficiency into the investment. And so the need to have the right compute and the right memory at the right time is that much more important. And so cloud customers are really driving to extract as much value for their deployed infrastructures as possible. And what that drives is a significant degree of, we call it blurring of the lines. We sort of look at the traditional cache memory, bandwidth memory, and fast storage as something that's been around for some time, but those memory lines are blurring. So, for instance, bandwidth memory. Bandwidth memory to cache memory, you don't bring a say DDR4 RDIMM and easily connect that to a GPU. It just doesn't. It isn't the right tool for the job. This is a requirement that drives significantly higher bandwidth, significantly higher performance from the memory subsystem, and therefore drives a very interesting blurring of the line between that bandwidth. Another blurry line, bandwidth memory and fast storage. We see a bifurcation around that traditional memory footprint, and the sort of drive to optimize cost and memory footprint is driving some interesting decisions across that boundary, and even within the bandwidth memory boundary. So the ability to optimize capacity, the ability to expand bandwidth where required, the ability to optimize the system configuration where required is really starting to really drive some interesting changes to the established hierarchy. And then, of course, Roger's going to talk about some of what's happening in the fast storage, where you see SATA moving very quickly to PCIe Gen 5, and you see capacity storage moving very quickly from hard disk drive to PCIe QLC. So 25 years ago, nobody drew a hierarchy like this. This was essentially memory and storage. And today, or just around the corner anyway, we believe that hierarchy looks something like this. And to Raj's point earlier, we believe the long-term view is that the memory hierarchy will keep extending. So this industry is driving a data center that's composable with extensive optionality. And it's a lot less deterministic than say it used to be even a couple of years ago. So we'll continue to look at all parts of this hierarchy to apply various aspects of new and interesting memory and storage technology. But we'll work a lot at the technology level, which Nago's going to talk about, and at the same time work directly with our end customers, as Raj had stated, in the ecosystem and infrastructure levels to make sure we get this right. It's a long-term vision that's really defined by the workload-driven decisions, again, in the search for that ultimate efficient platform. For near memory, we added this striation here with respect to comparing it to the previous foil. Near memory is the ultra-wide memory bus. This is essentially the trends here are HBM, high-performance memory. You can think of HBM2, HBM2E, and HBM3. And all of this is evolving in the span of about 4 years. And that's compared and contrasted to the evolution of bandwidth memory, which happens probably more like twice the time frame as that. And so what we're seeing is higher capacities, the need for much, much higher bandwidth, twice the amount of bandwidth in the second generation as in the previous generation, and a TSV-enabled stack of memory sitting directly next to an ASIC. This can't be a DIMM-based memory that signals through a connector. It would just be simply too much power, and you'd have to do a lot of infrastructure improvement around it, such as the cooler thing. So it really is a purpose-built memory that today looks at something like a 25 nanosecond, very fast turnaround latency. And that's really required because you can't economically, feasibly build additional cache onto standard server CPUs. It just doesn't, it isn't cost effective to do that. And so you've got to really rethink about what kinds of memory related infrastructure you need to put in place to be able to service workloads around the corner. With bandwidth memory, Mal's going to go into a pretty good detail here, but what we're seeing here is x86 CPU core count growth on the order of about 25% CAGR over the next several years. This is driving much larger need for both larger memory channels, so going from 6 to 8 to 10, and much faster memory, going from DDR4 at 3200 mega transfers per second up to DDR5 at 4800 and beyond. And there's no slowing down. There's some significant acceleration in this space as well. And again, driven by what's happening in the compute side. There's also a real push to balance memory capacity to memory bandwidth per core. And we're actually seeing this for the first time, some bifurcation around some of the market wanting to go to a binary density versus some of the market wanting to go to a non-binary density to, again, optimize efficiency and match capacity per core, nothing more, nothing less than what the workload really is. There's also a good degree of focus on racks, and this is reliability, addressability, and serviceability on the server side. DDR5 drives a significant degree of uptick in terms of RAS capability, and it's really due to the fact that customers are putting a lot more memory in the server than they used to. That memory footprint is large, and we've got to think about blast radius, and if something goes wrong, how do you sort of tolerate faults while still being able to move forward in your and do what you need to do from a workload perspective. The latency break here is about 50 nanoseconds or so in bandwidth memory. But what's interesting and what we're here to talk a little bit about to you today is actually what's happening in the layer just below it. There's a lot of excitement around CXL, and that breaks the architectural determinism in a couple of really interesting ways. It actually provides, really for the first time, the ability to optionality, to drive optionality into the system, and to balance cost, the capability to capacity. CXL enables memory subsystems to sort of grow at the rate that tomorrow's problems require, and we're looking at sort of all memory technology with respect to that. It's not it's not just a single memory technology that we're focused on here. So a lot of really interesting nuances that we explore when we look up and down this memory storage hierarchy. And with this greater optionality, and this coincidence sort of blurring of the lines, we can start to imagine what the future data center could start to look like. So we discussed, optionality in memory tiering top memory workloads that typically happens at the server level, the sort of sled or pizza box level, if you will. But this translates up to, to the rack level pretty quickly. And even you can imagine and stand back a bit and say, well, if we can do this and start to apply it with what's the innovation happening on the connectivity side and on the networking side, we can start thinking about how this really changes the makeup of the entire data center as we know it today. We know that workload and cloud evolution has driven the need for composability and optionality, again, that we're seeing at the server level here in the next couple of years. And CXL has really driven and emerged as an ideal framework to basically make that reality here in the next several years. So it's pretty exciting about what's possible here. Okay. So what are the benefits of CXL? There are many. First of all, the benefits of CXL are extremely compelling, particularly given when you look at the deterministic nature of what servers are, what the makeup of servers are today. Again, with bandwidth expansion, we've got port counts growing with what they are. Some of these port count growths are really outstripping the ability for the main memory footprint to keep up. And it stands to reason that memory bandwidth expansion, or some way to get more memory bandwidth into that core and be able to feed the beast in a different way, needs to happen. And we believe CXL really provides that avenue. We believe that that additional memory channels will do the trick in some cases, but folks are going to need much higher degrees of the ability to feed that bandwidth to the core that needs the bandwidth. The capacity expansion, another really interesting case here, and that really takes two roads. First road is really for those workloads that require significant degrees of memory. And what I mean by that is very, very large sort of main memory footprints. And it's a workload that wants even more, right? It's a workload that's attached to a QoS metric that says as much of the data that I can keep in a hot or a warm area, my workload basically runs as efficiently as it can, and I'm willing to go and pay the extra cost to associate myself with a much larger memory footprint than today's servers can supply. The other fork in that road is essentially what's going on over the next couple of years, where data rates on the server side and the main memory footprint are increasing in such a way that there will be pretty quickly the inability to signal to two RDIMMs, two memory slots in the same channel. We'll have to go to a single memory slot in the channel here pretty quickly. And if all else being equal, that single memory slot will then have to double in density if you want to drive the same memory footprint. And so what folks are looking at is looking at CXL to provide that pressure release valve, if you will, the ability to push that memory footprint, not just onto the standard memory footprint, but into the CXL bus as well. And so very interesting workloads that are looking at spreading that work across multiple memory or multiple memory tiers within that footprint. That's really the sort of two-socket memory expansion, if you will, from a benefit of CXL. We can also think about multi-socket benefits. And so what we're talking about here is multi-nodes, 2, 3, 4, 6, 8 nodes, potentially accessing the same pool of memory, if you will, as all simultaneously, essentially. And again, enabled by CXL. And in that regime, you're looking at a single server that is deployed with the standard memory footprint. And whenever it needs, whenever the workload needs to drive and grab additional memory capacity, it does so out of that memory pool. And the fabric manager is smart enough to know, okay, that the memory pool is associated with part of that memory, it's associated with node 0, and I'm going to portion that memory to allow node 0 to access it as long as it wants. And at some point, when it doesn't need it anymore, that memory is returned to the pool, and essentially the end goal is to significantly reduce what's called stranded memory, and obviously memory being a significant resource and a precious resource in the data center. So lots of really interesting ideas, lots of paradigms that are really coming about just as a result of CXL.
Hey, Ryan, real quick. I know I'm a big supporter of CXL itself as well, and kind of the direction it's moving. Is there any type of can you draw some correlations on, I know, the 3D Crosspoint and Micron pulling out a 3D Crosspoint, and the way Intel was kind of architecting that into, obtaining the PMEM structures. There was a lot of things where you had to kind of rewrite your code to take advantage of, kind of PMEM the right way. And from what I gathered, CXL is completely, it's kind of a different way of doing the implementation, so you don't have to really kind of rewrite to take advantage of that. Is there any things you can expound on that? Because I think that's one thing that folks are really going to kind of want to get out of this as well.
Yeah, absolutely. Thanks for the question, Jason. Yeah, we're under no sort of illusion that they're just moving to a CXL enabled memory is going to be a slam dunk. There still will be a lot of ecosystem work to be done there. Nonetheless, we believe that the latencies that we're talking about with respect to memory technologies on the CXL bus are close enough to that of DRAM that we believe the software lift will be significantly lighter when it's compared to other technologies. That's not to say that we aren't looking at a number of other technologies. We are, but if the latencies are closer to that of DRAM than they are to that of storage, the software lift is lighter. Now, from the perspective of persistency, that's something that we're also following very closely. It's a very interesting aspect. We find that with persistency, right now the market, it feels like the market doesn't know exactly what to do with it in a lot of ways when it comes to persistent media on, say, in a memory regime. And so PMEM is obviously helping that out, and some software out there that essentially is a virtualization or shim software that helps that aspect. But we're certainly looking at a number of technologies, and CXL is a key path to enabling some significant PMEM. So who's excited about CXL? Pretty much everyone. And we're excited about it because it's really, for the first time in a long time, it's large-scale ecosystem innovation happening on an x86 platform. And if you think about that, it really becomes very interesting because you can tap into what basically is 90% of the incumbent CPU slots as they exist today. And the specification is moving faster than PCIe did. There isn't a small number of firms sort of backing this drive. It's CPU vendors, it's memory innovators, it's cloud customers, it's server OEMs, it's software vendors, all basically after the same thing, which is working to optimize CXL to deliver as much of the needed optionality that frankly has been probably required for the last 15 years to deliver value to the entire ecosystem. It's not just a single player here. Everybody stands to win here. What's more is that CXL actually consolidates a number of fragmented efforts, and most times when efforts, albeit individually, kind of mean well, the fact that they're fragmented means that individually they don't move the needle as much as collectively they perhaps can. And so what CXL is driving is sort of aligning those efforts and merging what essentially is mostly the goal of these other disparate efforts into a common goal, which is a standardized CXL interface. In summary, we think composable compute architectures are absolutely needed to address this constantly shifting landscape of today's server workloads. We don't know what's coming around the corner. We know that optionality is absolutely going to be required, and the compute requirements that are driving or that are supporting the next generation workloads in turn drive significant changes into the memory and storage hierarchy as much more demands are placed on the memory technology in that hierarchy. again, things like latency, higher bandwidth, higher capacity, different form factors. And we believe that CXL provides the capabilities that have not yet before been, possible. And is perhaps the key element to realizing the data center of tomorrow.
I have a question about CXL and memory. So if you're going to be disaggregating memory across a CXL network, and if it's using PCIe 5, won't that be a lot slower than current memory technologies?
Yes, the latency there will be a latency adder, and there will be likely some erosion of some bandwidth there. But the idea here is that we're providing that CXL is providing an abstracted interface behind which we can do a lot of really interesting innovation to get a lot of that back, and as it sort of balances out between TCO and the memory media capability itself. And so what you're focused on is really a mix of how that media is optimized and what kind of performance you can provide the system on a sort of cost optimized basis, if you will. So yes, there will be a latency adder, but that adder won't be to the detriment of many workloads, given that that workload can span the domains of a more expensive memory footprint versus a more cost optimized CXL.
I have another question about memory expansion in general. I mean, so there is no modification to the application, but how the application can understand that is writing to local memory or remote memory, and just to manage the performance. I mean, maybe the application can decide where to write, so it can have different types of data stored in different segments of.
Yeah, that's correct. So there are multiple approaches to that. Approaches to essentially driving sort of a flat address space and essentially treating your main memory footprint and your CXL memory footprint as the same block of memory. There are also areas that require potential kernel adjustments. And there are also the approaches that really go into the application space, which is much longer pull in the tent over the long term. My colleague Steve Pulaski says that those types of software changes take 2 Olympic cycles to transpire. So those are much longer in terms of when those will become optimized. But for the right workload that stands to benefit significantly from memory connected CXL, we believe those workloads and that software will be adjusted and will be modified to accommodate CXL connected memory in a pretty significant way. And of course, when some of the customers own their own stacks when it comes to hardware, middleware OS and the apps that run on top of it, if there's a benefit there, they can move fast.
Yeah, thanks, Ryan. I think, Enrico, great question. We kind of always answer this generally from the perspective of an application and whether you get an opportunity to pin, portions of the pages or use it as flat or caching mode. The other way to also look at it, I think, is look at it as an infrastructure optimization play, right? When you're not talking about a big, large in-memory database or a single application benefiting. You're talking about TCO of an infrastructure, right, which hosts multiple virtual machines, and now you have more memory capacity. And if you have the smart ability to discern, what I would call VMs that need lesser bandwidth or can withstand higher latency and can operate out of the slower memory portion of the memory, you suddenly have VM density go up for certain kinds of VMs. And so that is an infrastructure benefit. Independent of kind of obviously assuming that the application you're running inside the VM can sustain the performance level. So we look at it as kind of traditional infrastructure that we find in enterprises, as well as shared multi-tenant infrastructure that the memory capacity helps bring a TCO benefit. than not having the memory or adding very expensive memory, and the rest, your other option is go out to storage.
So CXL seems to pretty much have a lot of support with a lot of vendors. There are competing standards from some vendors that for doing something fairly similar. What do you see as being the major advantages of CXL? Do you see it becoming pretty much the standard that everyone will adopt, or are there some things that it's good at that other things are better at something different?
Yeah, I think the single biggest advantage we see with CXL is the degree to which all aspects of the ecosystem are behind it, and not only individual members, but the depth of the membership of each of the individual groups as well. Everybody seems to be kind of walking in lockstep toward a common end goal, and like I said, to your point, there are other efforts out there that are trying to achieve a similar goal, but just don't have the kind of momentum, don't have the kind of wood behind the arrow, if you will, to drive the things they need to drive into the ecosystem like CXL does.
And I think, Justin, as you've seen very publicly, some of those like C6, OpenCAPI, I mean, there are bridges being built to understand the value of combined ecosystems, right? Where, as Ryan said, the investment goes in. And then if there is a feature or two that is missing, instead of that farming off a completely separate ecosystem, is how to best incorporate. The approach to CXL is let's bring the entire industry together and incorporate all the features we need, versus this being proprietary or tied to only a certain set of folks. So that is, I think, the big sea change from 4 or 5 years ago. We had OpenCAPI, C6, and you name it, and there were multiple people trying to do the same thing, to now what we see as a convergence around CXL, and the value of those other efforts is to drive things back into what we call the most prevalent standard, which we see as CXL. And this is the same story that has played out on the software side. We had OpenMP, and then we had OpenACC, and OpenACC then fed very interesting things to support accelerators back into OpenMP to support OpenMP, and now OpenMP supports heterogeneous compute. So that's how the ecosystem has worked successfully, and we see the same thing happening here as well, with CXL being the convergence point.